recording. We've been on chapter 22. I just wanted to have a quick review. Oh, before I forget, you better have whatever vaccination, there's a deadline for vaccination with a Pfizer. You better have it all done because October 6th, Wednesday, is our first test and you have to be live. And anyway, for you, you already have to be live for GH and GH2 and GH3. So I guess for you, it's not an issue, right? All right, so let's go on. We are talking now about electric circuits. We have spent quite a lot of time with this language of electric field and how when there's an electric field, then your whatever charge, Q0, in the presence of this electric field will now be shooting off in the direction of the electric field, and this electric charge Q0 will now have higher, will have what you call electric potential energy as a result of this force due to the electric field E. And by work energy principle, you can then say, hey, there is this much electric potential energy that now this charge has because it's been pushed, it has acquired energy. And this energy, the language we now use is to say, I want to look at this per unit charge. So that it doesn't matter what is the amount of charge I have now this much potential. So we have this language of potential, electric potential. And the electric field goes from a higher potential surface to a lower potential surface. That's how the electric field is directed. So those are the language that becomes into our daily life. And we now want to deal with electric circuits because I am now going to connect one end of the battery, of the capacitor, one end of it to the other end. And when I connect something between a positive terminal and a negative terminal, a current will flow. Why? Because my wire, there are lots of electrons in the wire. Well, when they now say that, gee, you have positive charges on this side, then the electrons are from this side are attracted to you, so they will flow this way. But according to Ben Franklin's definition, it's a current, a positive current that flows from positive terminal to negative terminal. Well, we now want to give a concept to it, which is the rate at which how many charges have moved across from one end of the circuit to the other end. That we now call current. And it is the number of charges that went across the surface per unit time. And the unit is amperes, and it is this French physicist who is an autodidact, which somebody told me last time, but I have confirmed, is somebody who taught himself, self-taught. He's really a very good inventor. And he gave the language of what you call classical electromagnetism. So we now are dealing with electric currents named after an ampere. And you have also to distinguish in our daily life between direct current, which means that it is a flow in one direction. And as I mentioned, when you have a solar panel, the electricity that you get by the solar panel, they are DC currents. They are currents that have no flip-flop, flip-flop, flip-flop. But for the current that is generated at the power station in the hydroelectric plant, at Con Edison plant somewhere, they use what we will later learn in terms of Faraday, induction, Faraday's law of induction. There, the current that is induced by this magnetic field, you have a coil, then the current that is induced flips. It zips across, zips back, zips across, zips back, zips across, zips back. And in United States, it is 60 hertz. That is the, or is it 50 hertz? I don't know. I'm not in the industry. I think, does anybody know? The AC current, how many hertz is it? 50 or 60? You can check it yourself. But in Europe, elsewhere in the world, it's the opposite. I think elsewhere in the world it is 50 hertz, whereas in this country it is 60 hertz, because Mr. Edison decided it was 60 hertz. Did anybody check on the Google? Anyway, so we have to distinguish between DC current and alternating current, and we will come to it. But first, just to get a idea of how much charge is involved, if you have a 3-volt battery, which is sort of like a pocket calculator, and we know that the current is milliamp, 0.17 milliamp, the question is, in 1 hour, how much charge has come in? Or how much charge have you used up? Because that's what my phone, you have to worry that you charged it, but then, after a day or after so many hours, it says, 5% power. It is very low in power. Well, you can find out how much if you know the current, and they say the manufacturer tells you that the kind of current that's involved for this pocket calculator is 0.17 milliamp, and after 1 hour, the amount of charge that has been used up is 0.6 coulomb. But then you would also say, how much energy has this battery supplied to my calculator? Well, you now use this formula, and at first when you look at this formula from just not thinking about it, it's not unreasonable to say energy is charge times energy divided by charge, because just by the ordinary rules of you can cancel out charge. But this actually is the work energy principle that we mentioned earlier. You remember, I have this electric field. This electric field is now forcing whatever charge I have, Q0, to go a certain distance in the direction of my electric field, because the force is Q0 times E. But then as a result of that, the electric field has done work on you. And by work energy principle, that means that your electric potential energy, it went into electric potential energy. Just like if I lift this book and I applied a force mg, and I lift it very slowly so that I do not give it kinetic energy, the work I did went into gravitational potential energy. Well, here it is the electric potential energy. So this is that basic work energy principle in the language of potential. Electric potential is electric potential energy, which is the total energy divided by Q0. But now they want to know what's the total energy that these charges have when they went. The battery supplied this much energy to this calculator. Well, then you now say, okay, from this, I can now do the calculation. I've already figured out this 0.61 coulomb, and you told me that it is 3 volts, that the potential difference between the anode and the cathode is 3 volts. Therefore, the total energy is 1.8 joules. That means that my battery supplied this much work. Okay? I mean, this is just to get used to the language, because after all, you carry your phone, and your phone does use up the charge that has been charged. Originally was 100%, but now it is 5%, 3%, 2%, and you would like to know what has been involved. But now, in this chapter, we now want to introduce circuits. And so circuits is one where here is my battery. Positive, in the language of these electrical engineers, they'll put positive as a longer line and the negative is a short line. The current will flow this way, even though the electrons actually is flowing the other way. But that's the language. And if you now have a circuit, you then have to have this concept of resistance. It is the actual current that flows, proportionality with the voltage, the voltage difference, the potential difference. The higher the potential, then there will be higher the current that flows. I mean, you can understand that, right? The higher the potential voltage, the bigger the current, and then the proportionality is what we now call ohms. And we already went through this poor guy who actually invented galvanic circuit and published it, but nobody really accepted it. It somehow was the way he presented it was not the way we now say it. It was more involved because he was trying to understand and explain all the things inside this voltaic cell, galvanic circuit. So it wasn't well presented. And poor guy, his college did not appreciate the work, and he had to resign from that because they didn't up his pay, right? And so he went to this Polytechnic School of Nuremberg, and even there, he was not well appreciated till about, 18, 19 years later. Then they made the University of Munich, which is the big university, offered him a professorship. Anyway, there's the Ohm's law, and we now can do simple calculation. This is very simple. You say, I'm told that this flashlight uses two 1.5 volt batteries in series. Therefore, the total voltage for this flashlight is 3 volts. And I'm told my engineer assistant has already measured the current that flows is 0.4 amps. Therefore, you can say, I now know that the resistance is 7.5 ohms. You need to know the resistance because it tells you if you now were to, instead of using this 1.5 volt battery, somebody connected this flashlight to the car battery where the V is 12 volts. Then the question is, what's the current that flows to my poor filament, the filament that is inside this bulb? Well, what happens is then, because your voltage is not 3 volts but 12 volts, it's 4 times. And if it is 4 times, later we'll find out, then this torch flashlight will burn out. This filament will burn out, and we will see how or why. All right, so this exercise, when you tell me what is the voltage and when you tell me what is the resistance, then I know the current that flows. And it is important to know what is the resistance of your filament. And now for the engineers, they would actually need to know more fuzzy aspect of this resistance. What's this fuzzy aspect? And that is that your cable, after all, the transmission line came from Niagara Falls all the way down here, I don't know how many miles, a few hundred miles, right? When they come down these few hundred miles, the resistance is proportional to the length. The longer the cable or the wire, the more resistance there is. Why? Because these poor electrons, they are knocking themselves silly as they come down from Niagara Falls. Because the electrons they bang into other atoms and electrons and atoms and electrons. So they are being banged all over. And the longer the wire, or the more of this resistance there is. So the resistance is proportional to the length and is inversely proportional to the area. Because if the area is big, then there's less banging. It's like when you make this very, very tiny, oh, then they will bang, you're squeezing them all. Think of it this way. You are, sort of an army of little soldiers, and you're coming down the turnpike. But if you now make this wire smaller, well, then what happens is all these poor guys, they are being squeezed, and therefore the resistance goes up. So R, they, for the engineers, they now say it is resistivity, which is a constant, depends on what material it is, and it is L over A. L being the length of the wire, and A being your thickness of the wire. All right. And the engineers, they have already measured it. They tell you if it is aluminum, is this resistivity. If it is iron, it is this resistivity. And you can see which one is higher, mercury, tungsten. I'm not an engineer, so if there is any question involved, you can just look it up the table, right? So, but for us, the concept is here that the resistance of a wire is proportional to the resistivity times L over A. All right, so this is the key thing, and I always color code it so that we can know how to use it. Not that we remember what is the resistivity. Okay. And now here is a common household question, which we all need to be aware of, although most of us take it for granted. Namely, if I need to, well, this one says electric lawnmower. If I need to have some appliance and then plug it to the wall, but the wall outlet is over there in the other end of the room, and I need to now get an extension cord, right? And we don't think about it. We just simply say, gee, I have, tens, I wouldn't say hundreds of extension cords, but I have, multiple extension cords all over the house. So I can just plug it in and then use it. Well, there is a question, what gauge, they call it. These are the engineers. I'm not an electrician, but the concept is what I wanted to emphasize. That there's a difference between what they call a 20 gauge and a 16 gauge cord. What that means is the extension cord, what is the thickness of your extension cord? If it is the 20 gauge, it is 10 to the minus 7 in these units. If it is 16 gauge, it is higher. The cross section is higher. Now, what they are trying to show us is that if you want a long cord, it's better to use a thicker extension cord. Are you following what I'm saying here? If you need a long, like lawnmower, you need a long extension cord because your outlet is somewhere in your garage and you are, using the lawnmower out in the lawn. So you need a long, extension cord. For those long extension cords, you better use a thicker. Thicker means that A is bigger. And when you use A is bigger, then your resistance would be less. All right. And you want to have the resistance less so that there is no potential for energy loss, number one. Number two, there can be issues with your rug. If I have a fancy living room, and I have a carpet, and now I just anyhow plug in a extension cord where the cord is very thin. What happens is that the resistance of that extension cord then is higher. And when it gets a little too high, we will see later today that you can actually have electrical fire. You will know, we better be aware that there are these fire hazards around the house. All right, so it is all in here. This basic formula, the concept is there, and the book actually, they do it for you, and they say, oh, given that it is made of whatever, resistivity is this much and the length is this and so on, the resistance 1.2 ohms, versus for the thicker wire it is 0.99. All right, that's just for this particular example. Now this I don't know, impedance plethysmography, I have no idea, but apparently biomedical devices, they can actually measure the, what is this, the voltage difference. I have not been subjected to that measurement, I don't know. They're interested in the voltage between this part of the thigh of the leg and that part of the leg. Does anybody know what is this for? Impedance plethysmography, I don't know. Let's go on, because that's not for us, not for me. Apart from the concept of. But now, this concept of resistivity, it's also dependent on temperature. After all, you know, you can use these electric cookers, and the electric cookers use high resistance. They want to have high resistance precisely because they want to have more heat coming out. And there, the resistance of the coil itself depends on temperature. And this, again, the engineers, they have measured it. You don't have to worry, I don't have to worry. All you know is my electrician installed this electric oven for me, a boiler for me, or this, what do they call it? The plate, they call it something name for it, something plate. They have installed it for me, and I know that the manufacturer has made sure that the coefficient of linear temperature dependence, the expansion, is within the safety limits of this oven. Okay, but now what we want to now come to is this concept of power. We already have voltage, we already have current, and we have understood that there's a relationship between the voltage and the current by this resistance, ohms. And now we want to say, supposing I have so much charge flowing through a battery where the potential difference between the terminal is V. You want to know how much power. Well, the amount of power is, first you say, is the energy. And as I keep mentioning, when you have the charge times the potential, electric potential, you're measuring the amount of electrical potential energy that you have in this battery. Well, if that is the energy used, the power is the rate at which you use it. Because I used up so much energy, so many joules, in 3 seconds. Then the power is the energy used over 3 seconds. But when you now re-express this, this becomes delta Q over delta T times V. So it becomes this very simple but very important formula. Because this now says, you want to know how much power is consumed or supplied by this battery. If you want to know how much power is supplied by this battery, you measure the current that flows when you connect it and the voltage of your battery, V. Then the power is I times V. If you use I in terms of amps and V in terms of volts, then automatically I times V is the amount of power, so many watts. All right. So the key formula for this concept of electric power, now that we have V equal to IR, Ohm's law, this one is very important for all of our appliances. For your electric oven, you will then look for the manufacturer's user manual, and they'll tell you, this one you supply or you use it at a voltage of 220 volts, and it is the current that it draws is I don't know, so many amps, let's say 15 amps. Therefore, the power is so many watts. Or actually, what they tell you when you look at the electric oven, they'll tell you this oven is rated at so many watts. So they will tell you it is 15, let's say, it may be mega, I don't know how many watts, 1500 watts. So they will say it is 1500 watts, and the voltage that you use it for is 220. So they tell you what is the power, they tell you what's the voltage, they don't tell you what's the resistance. They don't tell you what is the current. I mean, if you have a ammeter, you can measure it, but when you get an oven, they will tell you this oven is rated at, namely it's been measured and constructed such that it will consume 1500 watts, and you should plug it into a power supply which is 220 volts. And now the unit for power is watts, and most of the time you can now express it as I times IR, which is I squared R, so that the key thing for the power used is the current. You say, yes, it is current times voltage, but since they are related, it is oftentimes more direct to now say the power that is used by my oven is proportional to the current squared that is flowing inside my oven. All right, that's a key formula, and we will come quickly to that, but let me finish this. But the other one is to say, if I want to now not express it in terms of the current, but in terms of the voltage, then I is V over R, so this becomes V squared over R. So there are two equivalent ways of saying what it is, but the thing that is important is the manufacturers tell you the power rating, and then it's up to you to supply whatever is the voltage, or up to you to draw whatever is the current. And when you now have your microwave oven, which you happen to have bought shipped from Europe, I don't know anybody who would, but nowadays with the global trade, what you think is manufactured in US, it may have been manufactured in Europe somewhere, or in Asia somewhere, right? So when you now ship this microwave oven to you, it is rated at, let's say, 1500 watts. But it is rated at 1500 watts and designed for 220 volts. But in some places, like in some places in America, we don't have 220 volts, we have 110 volts. Now, if that's the thing, then even though this microwave oven is rated at 1500 watts, when you use it, when you plug it to your household circuit, if your voltage is not 220 the way it was designed and manufactured in Asia or in Europe, then when you use it, you find that it is not at the 1500, it's like 400 watts. That means that I'm not cooking what I thought I was cooking. Are you following what I'm saying? I may have. Are you following what I'm saying? Yeah, you see, so it is, in a way, what the manufacturer tell you is the power rating. They say this is 1500 watts, but if it is 1500 watts according to what they assume the microwave oven is to be used for, and if it is for European, standard, then their voltage is, let's say, 220. Whereas you bought it rather, and then they shipped it and they did not ship the right one to you because they have such a lot of shipment, and some of them they got cross wire somewhere, and you then got this microwave oven, a brand name, but it turns out to be actually, even though it's rated for 1500 watts, the voltage is not meant to be used in this country but meant to be used in Europe. Then what you find is, I didn't get 1500 watt, I get 400, or I mean a fourth of that. So this is the key concept or the key formula that we all need to be aware of. And now since we have this formula in front of us, we also want to now take the example of this filament. You remember we had this picture of this flashlight. Whoops, where's the flashlight? I have the flashlight. Didn't I have the flashlight? Yeah. You remember I have the flashlight. Now, if I have this flashlight, and now inside it is this filament, and we have been told, or we know, because they told us what the resistance was, we know that it is 4 amps that flows in here, right? 4.4 amps. But if now I gave it a big voltage, instead of what was this here, 1.3 volts, I have 110 volts. If I put 110 volts onto this poor lamp, this flashlight, if I put such a big voltage on it, the power consumed by this filament would be V squared over R, or I squared R. But the R remains 7.5 ohms. The filament, the resistance, by the way the wire is made, it is only 7.5 ohms. But you put 110 volts on it, the current now becomes very high. And if the current becomes very high, the power consumed by this filament in the lamp is I squared R. Well, R is 7.5, but I can be like what, 10 or 20 or 50 amps. This thing would burn out. You see now how I squared R or V squared over R are very key concept of power consumed. And in this case, this is where the filament burns up. And so we need to be careful when you design a house and you now have circuit, you allow for circuit, and you design, oh, you're not architects. I confuse you. But when you have your house, beware when you have these extension cords, when you have these curtains around, beware that the current flowing in your circuit doesn't get too high, because I squared times R, you can in fact cause some electric fire. All right. So let me get back to where I was. Where are we now? Yeah, okay. Oh, I didn't get to honor the unit. We all know it's watts, and actually you already know the unit watt, because in 203 we already learned about the power measured in units. But this is James Watt, and he actually had there's a story. I I wanted to I got it out of this Wikipedia. There's a popular story that Watt was inspired to invent the steam engine, because the concept, the power, the unit for steam engine, James Watt is famous for steam engine. And the story is that he was inspired to invent the steam engine by seeing a kettle boiling, the steam forcing the lid to rise, and thus showing Watt the power of steam. Because you have, each time you cook a pot of water, and if you were to cover it, when the steam is building up, the cover in fact rises a little, right? Watt did not actually invent the steam engine, as the story implies, but dramatically improved the efficiency of the existing Newcomen engine by adding a separate condenser. Anyway, the name Watt is now. Okay, don't worry about this. Okay, so now, we already did that, didn't we? Or we haven't. If you have this flashlight and you are told that the current that flows is 0.4 amp and it is 3 volts, then immediately you say it's 1.2 watts. And you can now figure out how much energy has been dissipated in the bulb in 5.5 minutes. It is 400 joules. Well, these are just making use of the formulas. But now we want to come to this distinction between the DC and the AC. As I mentioned earlier, when you get the electricity from, let's say, Niagara Falls, they have a waterfall down there, and then the people have made use of this coil which turns in the presence of a magnetic field, and we will learn later about this Faraday's law. But anyway, the electric current that is generated is not a DC current, but it goes from positive to negative, from positive to negative, from positive to negative, meaning those poor electrons, they are being zipped back and forth all the way from Niagara Falls down to New York City and back. They have to make that trip. Poor guys, yeah? But anyway, that's what the current is. It's an AC current. And now this AC current, you can plot it. You can say, as a function of time, or at some instant in time, there was no current. The voltage was 0. But then it rose, and then it came back down to the negative and up, and this V0 is the maximum voltage of this supply that this power plant is supplying. Okay, and if you were to write it as a mathematical formula, you would then say that the actual voltage that came down my wire is whatever's V0, but sine omega t, where omega we now write it as 2 pi f t. You remember this notation for a wave, right? Sine omega t. So this now is the frequency, and the formula for this voltage now as a function of time is just simply V equal to V0 sine 2 pi t. Well, in a circuit, if you have this voltage, then the current is simply directly proportional to it. The resistance is not a function of time. Resistance is whatever's the resistance due to the material you have made this wire out of. It has a definite resistivity, it has a definite thickness, cross-sectional area, and you already have a certain length L. So the resistance is not a function of time. Therefore, the current is in phase with the voltage. When the voltage is big, current is big. When the voltage is small, current is small. And so the current is V0 over R sine 2 pi ft. And you can now say that is I0 sine. V0 is the peak voltage and I0 is the peak current. Because the current goes up and down, up and down. The voltage goes up and down and up and down, and they are in sync. Because when the voltage is big, current is big. When the voltage is negative, the current is negative. All right? And so I'm interested in what's the power. And Con Edison, of course, is very interested in power. After all, they say, we spent such a lot of money building this power station. We have to maintain this transmission wire. And after all, we need to make money. And we supply you with power, with energy. You better pay. And they will decide. I don't know what is the rate that they charge you at, but it's you have to look in your power bill, and then they will tell you per kilowatt hour, either it's 12 cents or 13 cents or 14 cents. And with economy, it just keeps rising, whatever. But it's about 12 cents or 13 cents per kilowatt hour. Okay, so here is now the power, and it is I times V. But now we put in I0, V0, then it becomes sine squared. And now you can see that the power is now itself a function of time, right? Because it's sine squared. So it will now say, at time t equal to 0, I'm not drawing any power. But then at a little fraction of a second later, gee, I'm drawing a lot of power, I0, V0. Then, oops, again it came down to 0. Then it went up and came down to 0. And Con Edison is not going to say, hey, I want to collect each time you hit this peak. Because this thing is going on at 50 or 60 hertz. So all they do is they measure the average power. And they say, on the average, I had to supply you with so many watts. Please pay according to so many watts. And actually it's kilowatt hour. They measure it in units of kilowatt hour. Well, if you now take this sine squared, the average is half, because sine squared reaches 1 and 0 and 1 and 0 and 1 and 0. The average, of course, is a half. Therefore, it is now, if you express this way, you will then write the average power is I0 V0 over 2. And the engineers now invent a language. They call this the root mean square. They say that the root mean square current is whatever was your peak current divided by square root of 2. And the root mean square is whatever is the peak voltage divided by square root of 2. So that they got rid of this, because engineers don't like to have dangling factors of half. So they just simply say it is the root mean square current times the root mean square voltage. All right, I mean, that's just their language. Now, for you and me, since we are not engineers, no big deal. So when they Con Edison tells you that they supply you your household at the household voltage of 110, or is it 112, or let's say 110 volts. What they mean is that it's the root mean square, which is 110 volts. The actual peak voltage is square root of 2 times that. All right? And you say, no big deal, because I'm not the one who is so fussy and curious to know what is the maximum voltage and so on. But in these days, when you have all these computer chips, after all, my laptop, I don't know how many chips there are in there, but there must be a lot of chips. All these little chips, they are very sensitive. When the manufacturer, RMS, that's just a language. RMS is whatever is the peak current divided by square root of 2. Because if not, you would have to say it is I0 V0 over 2 from the original formula. And they just say, I don't like to carry this. So I will define this to be root mean square current and this to be root mean square voltage. All right, RMS means root mean square. Okay, and now I wanted to bring this up because you can say, no big deal. I mean, for me, no big deal. For you, also no big deal. But for the computer chips, for the people who manufacture computer chips, they are very sensitive. You know why? Because these little chips, they can only stand, I don't know, let's say millivolts. They can only stand, let's say, 0.1 millivolts. And if your voltage or your current, milliamps, if let's say it is 0.1 milliamp, if your current is over that, boom, my chip burns out. You follow me what I'm saying? So for the people who are in the computer chip business, they now say, oh, when the battery, whatever is the source, after all, you plug this laptop to a charger, and the charger is using the supply from Con Edison. So when they say, oh, this one is 110 volts, by the time it comes down to my laptop, the actual voltage across here, it makes a difference whether it is the root mean square voltage that is point whatever millivolts, or is it the actual, and it cannot stand anything bigger than point something millivolts. Am I making myself clear? You can get confused between I0 and IRMS. And when you use your charger on your laptop going anywhere else, you plug it into the AC charger. What matters to the computer chip is the maximum voltage better be within my design. If the maximum voltage is bigger than my design, kaput, you have destroyed my laptop chip, that particular chip. Anyway, I may have dwelled too much on that, but you'll be okay. Let me come back to here. So we now say V equals IR, but now the commercial reference, when they say this voltage is 110 volts, they mean root mean square, and current, they mean root mean current, root mean square current. And if you are sensitive to what is the maximum I, what's the maximum V, then you better remember that there's a square root of 2. But otherwise, the engineers, they continue to say the average power used is VI, but you have to use root mean square. And the power used now, you can really express it in terms of I root mean square, squared times R, and the power can also be expressed as V root mean squared, squared over R. I hope you understand. Just appreciate a little bit this thing about root mean square versus the actual maximum voltage in an AC circuit. Okay, so now we can do a quick application. If I have a stereo receiver and I have a peak voltage, and now you notice they are being fussy here, or maybe they are being cunning here, and they are saying, hey, my stereo receiver receives a peak voltage, which is maximum voltage, of 34 volts to a speaker. The speaker behaves as if it has a resistance of 8 ohms. Determine the root mean square voltage. Well, that's easy by definition. You divide by square root of 2, and now you'll notice there is indeed a big difference, right? The peak voltage was 34 volts, but the root mean square is 24 volts. That means that when you say that it came from my household circuit and the root mean square voltage is 110 volts, the actual peak voltage is more than 110 volts. It's 1.4 times that, 40% more. You understand now the difference? Yeah. And likewise, if you now want to know what is the if you want to know what is the current, the root mean square current, it is 3 amps, but the actual current, the maximum peak current, is, you multiply by 1.4, it's 4.2 amps. So there is a difference between root mean square and the peak voltage or the peak current. And the average power is I times V, root mean square, 72 watts. Okay, now this is the picture that I should have used. They say extension cord and potential fire hazard. And imagine that you have a house that has a heater and winter is coming. By the way, fall has already started at 3 o'clock, I think, the fall season. So we're entering into the fall, and it's going to get cold, and you will need a heater, and unless you have a central heating system, but if you don't, you want to have it near wherever you are, and you need an extension cord, because the actual cord that comes from this manufacturer is only this much. But you need an extension cord, and now when you have an extension cord, they are telling you, be careful. Why? Because your extension cord, there now is a resistance. And if you are using a heater, the current is not a small current, right? Because the voltage is the 110 volt. And when you have this long extension cord and you did not use a thick extension cord, instead you use a thin extension cord, because you were not careful, you didn't care, you were, I guess, ignorant, or will you say I was innocent? But there's a difference between innocent and ignorant. Well, if you did not know and you use a thin extension cord, this thin extension cord will have a high resistance, right? And when you have a high resistance, V squared over, what did I do now? I squared R. Yes, R is now big. I squared is whatever is the current that flows. I squared R. And now, when my current is big and my R is also big, this can cause a fire. All right? So just be aware that you should actually always use what they call recommended, namely a thicker extension cord, not a thin. Now we want to come to the things about electric circuits which are again, part of our daily life experience, because we never have a circuit involving only a single resistor. We will always have circuits where there are more than one device connected to a voltage source. And when we have more than one, the question becomes, how are they connected? And the series wiring is one where this is connected to this lamp, or this whatever appliance is connected to another lamp that has resistance in it. And I am interested now in what is the actual current that flows, right? Because they all came from a given source, and this source can be the household circuit, or it can be a certain battery. I would like to know what is the net resistance when I have two lamps in series, or when there's Christmas lights, you usually have more than two, you have maybe 100 in series. Well, if you have two and a current is flowing, then the voltage across this one is I times R1, because you told me the resistance of this guy is R1, and the current that is actually flowing is I, so therefore the voltage across here is I times R1. But then the same I is going into this resistor, so the voltage across here is I times R2. But now V1 plus V2 must be equal to the total voltage, because that's my my source, my battery. My battery has voltage overall of so many volts. Therefore, you can now say, since V is equal to V1 plus V2, this then says that for this thing, the resulting overall resistance is simply R1 plus R2. So this then is the very simple formula. The series resistor, they are simply R1 plus R2 plus R3 plus R4. If I have a string of lights and they were all in series, then the total resistance is the sum of them. All right. Now, have you ever tried to have such a string of lights? You know, because it's holiday season and you want to have those lights. Do you think that those string of lights that they sell you, are they in series? Or maybe I can ask the question differently. Huh? If I have a string of lights, you know, and they were connected in series, if one of the bulbs blew, you know, these little bulbs, they are so easily, the filament can blow up, right? Because it's I squared R, and if I is a little bigger than such and such, it will burn out. If I have 100 these lights and on, you know, for decoration, would I want them to be in series? Why not?
I guess because if one of them blows up, like everyone, all the others can still work. If you don't want it to be series, one of them breaks, and then that means all of them is not lit up also. That makes sense.
Yes and no. Because if one of them broke, no current can flow. Because this one already broke. There is no current that can flow now. You got the idea? Therefore, you don't want your season lighting to be all in series. You got the point now? Because if it blew, then there's no way for my current that came here and it was singing along, you know, and then it came here and says, "Uh-oh, I have no My lamp here has no connection from this end to that end because it blew, it melted, it actually just burned out. Then there is no current. If there's no current, all my 99 other bulbs don't light up. You know what I'm saying? And then you would be so frustrated because I have 100 lamps. I don't know which one blew. Would you know one of them, which one blew? It's not that one of them began to melt, began to have fumes coming out. No, no. These filaments, when they blow, that's it. No light from it. You see now the point? Therefore, when you buy this kind of a thing, the manufacturers will have already answered this crisis by not connecting them in series. Okay, and now we can go to, yeah, okay, all right. This one is just to go some more to figure out what that is. Well, you can work out the when you have this together, this is the total resistance, and you can then figure out what is the power used, is I squared R, and the total power, which is 10 watts plus 5 watts is 16 watts. All right, but since I'm already into this question of why it would be bad to have my holiday, season lighting to be all in series, precisely because if at some point one of those bulbs sort of like burned out, they didn't give off any fuse. It's not like there's a volcano fire that you can see. Therefore, you say, I don't know which one of them, and then have to take each one out and then separately test it. Take each one out, separately test it. I would say, forget it. I'm never going to buy this brand of lighting from them. Oh, this one is an application of what the personal electronic assistance, again, is by your resistance. You press on it, there is a certain resistance and the voltage. These are for the engineers. Okay, now we want to come to the alternate. The alternate is to do it in parallel. What does that mean? That means that I have this bulb and I have that bulb, and both are connected to this end. It's not like the other case where this one is connected to that one, so that R1 and then you have R2. Instead, this is one where I have R1, this bulb, and then R2, the other bulb, and they both are connected to the positive and to the negative ends. This is what you call in parallel. You see what is meant by parallel, right? You didn't connect this one to this one. Instead, you connect it like this. And you connect both to the negative side, the cathode, and this to the anode. So this is then in parallel. And now, what is the circuitry? What is flowing? What is flowing is from this battery, there's a current I coming out. And there are, 10,000, of these charges coming out. So I have 10,000 charges coming out per second or per millisecond. Then they split because some of them will go through this one, some of the others will go to this one. I have I, and it splits into I1 and I2. And now I1 will go over here, and there will now be a potential difference when it goes through, which is I1 times R1. I2, when it goes through here, will now have a potential difference of I2 R2. But they both must have the same voltage. Why? Because they came from this side, which is at 12 volts, the other side, which is at 0 volts. All right? So the voltage across here must be the same as the voltage across here because They were all connected to the same. And we are sort of, in the language here, we are saying this has zero resistance, there's no more voltage drop. So this then is what is called the parallel circuit. And there are many examples. You have your household where you have your TV, where you have your stereo, where you have your light bulb, and they all are parallel circuits. When you plug it in, it would be, this is your source, 120 volts. Each one are plugged into the same source, 120 volts. Each one, when you plug it in, it is at 120 volts. This one, you plug it in, it's also at 120 volts. This light bulb, when you plug it in, is at 120 volts. So this is an example of parallel wiring. This is just to give an analogy in terms of the pipe in the language of 203, but we already can see the analogy, and I want to come to the math aspect of it. You remember we said the current is split. It is I plus I2, but I1 is V over R1, I2 is V over R2, and it's the same V. Therefore, the total current I is V times 1 over R1 plus 1 over R2. So it's like V times the effective resistance. So for parallel resistors, the formula for parallel resistors is 1 over R effective is 1 over R1 plus 1 over R2 plus 1 over R3 plus and so on. All right. And the example of main and remote stereo speakers you are connecting. But let me come back to the lighting, holiday lighting. When you have a holiday lighting, you don't have just two, you have, let's say, 100. But they all are connected in the parallel way, namely all the lamps, the bulbs, they are connected such that one side of it is to the positive terminal or to the household plug. And when one of them burns out, when one of them, like the fuse blew up, then no current can flow. But no big deal, the current will now be flowing through the rest of them. If this particular guy conked out, the rest of them are still on. And so what happens is, when you have one of the bulb go off, it became dark, but the rest are still light. And though I don't have to now scratch my head and say, I have 100 bulbs, I don't know which one, and I'm going to be really mad at the supplier for giving me this lousy wiring. Instead, you say, oh, the fifth one, I need to change it. Okay, no big deal, I can change it. You see now the advantage for your household appliances and for these holiday lighting. You better have the right kind of wiring so that it is parallel wiring, and if any one of the bulb is off, there are those other 99 others that continue to get the current from my source, whether it's the household voltage source or the battery, and you can continue to sing along whatever you are singing, right? Any questions? Okay. Somebody had a question? Yeah. And now this is just the mathematical application. They say most receivers allow the user to connect to a remote speaker in addition to the main speaker. You see, let's say that this has a main speaker, but now you say, I want to have an extra remote speaker. And now when you do it that way, you should do it by parallel wiring. You don't want to have it as a series, because if something happens to your remote speaker, you can kill your original speaker, right? So they say they want to add a remote speaker to the main speaker. At the instant represented in the picture, the voltage across the speakers is 6 volts. Well, this is not a, yeah. And now they determine what is the equivalent resistance of the two speakers, the total current, and the current in each speaker, and the power dissipated in each speaker. In other words, you now go into the actual analysis of what happens. Well, since this is a parallel circuit, the total resistance is 1/8 plus 1/4, because this one is 8 ohms, the other one is 4 ohms, and the net result is now 2.67 ohms. You notice the speaker by itself, the resistance is 8 ohms, or this remote speaker by itself is 4 ohms. But when you put it in parallel, the equivalent resulting resistance for this whole circuit is now about 3 ohms. And if that's the case, you can now say, hey, I can figure out now what is the current that flows. Well, it is, you told me it is 6 volts divided by the equivalent resistance of about 3, then the actual current that actually flows in this is 2.25. The actual current that flows from the actual current I that flows to supply my two speakers, the actual current that flows is so many amps, 2.25 amps. And you want to know what is this now? Oh, what is the current that actually flows through here? 8 ohm. Well, it is 6 volts, because that is overall 6 volts divided by 8 is 0.75 amps. And through this guy, it was 1.5. That's why when you add the two, it is still 2.25. 2.25. So that 2.25 amp is split into 0.75 amp and 1.5 amp. And if you now want to know how much power is used, well, you just multiply the current through this first guy, and you then know it is 4.5 watts. Now, which one is 4.5 watts? Yeah, this guy is 4.5 watts, whereas the other guy is using up 9 watts. All right, I mean, that's just working out, making use of the concept and working out what the application is. Okay, now this is a very interesting example. I don't know about you, but in our house, the electricians now are very sophisticated, and they install these what they call three-way light bulbs. Do you have does any one of you have this kind of a three-way light bulb? There are 3 switches, you know. Have you ever worked with that? No? Yeah, you're not sure. Well, now we know enough to try it. Yeah, I have a 2-switch one, right? Yes, but this one 3-way lamp. And they show you how it works. So here is the circuit. This comes from the household circuit. You know, you have a plug in, so you know it is 120 volts, right? And now inside this lamp, there are 2 filaments, meaning 2 resistors. One is a 50-watt filament. The other one is a 100-watt filament, meaning that if you were to put a current through it, it will consume 50 watts, whereas this one will consume 100 watts. So for example, if you were to close this switch, A, you know, there are 3 positions, and if you were to close A, you are turning on 50 watt, which means that it's not so bright. Yes, it's not so bright. But if now you don't turn this on, you turn that on, you know, A and B and C. If you turn B on, you get 100 watt. You say, hey, it's the same bulb, you know, right? Of course, you have to pay more for this kind of bulb, but it's the same bulb. But now you close B, it has 3 switches. You close B, it is now 100 watt. It's brighter. But now what happens if you now have both A and B, namely the 3rd switch, both A and B? And now that's where we now can figure out and see the interesting aspect. You see what I'm talking about? A 3-way light bulb, and it is using parallel wiring. So if you turn on, press A, you get 50 watt. You say, oh, but it's not bright enough. I want to try the other switch and turn on B, it is 100 watt. And now what happens if I turn both? Okay, so now we go through the analysis, all right? And we now say, what is this now? It is the 24 volts. Yeah, you have to, you have to work out the, what is the resistance, given that it is 50 watt and given that it is so many voltage. This, you can sort it out. If I have the, yeah, well, yeah, actually I should have, I'm relying on them too much here on this particular slide. You can work it out for yourself. I mean, that would be the homework. When you have A and B together so that it's parallel, you can now ask, what is the new wattage? The fact that this is 50 watt and now you assume this is a certain voltage. I don't know, maybe you call it 24 volts or you call it 110 volts. Try it out yourself. Let's say it's 110 volts. Then when they tell you it is 50 watts, that means that the resistance of this is, you have to work it out. It is V squared over R, and it is 50 watts. You can figure out what is the R, all right? And then you also can figure out what is the R here. And the fact that it is 100 watt means that the R here is smaller because the voltage is still the same. Therefore, this resistance is smaller so that the power is V squared over R, right? So this resistance is smaller. And then when you now have both of them on, then the net resistance is 1 over this R plus 1 over this R, but this R is twice that. So therefore this is 1 over this R plus 2 over the same R, you know, because this R is double that. And therefore now the net resistance of the whole thing is smaller because it's 1 over R plus 2 over R. Therefore the net resistance is a third. And since it is now smaller, now the power is the same V squared over a smaller R, therefore it's brighter. Are you following me now? I wish I could write this down over here, but ever since my laptop has been updated with all these updates, I have lost my ability to write. Yeah, I have lost my ability to write. So Can you do it yourself? Do you follow what I'm talking about? Shall I say it again slowly? Yeah, let me say it again slowly, right? Let's say that it's 100 volts, not 110, because it's easier, right? Let's say it's 100 volts. Then the fact that this is 50 watts, it is, well, let's say 10 volts. It's easier. If this one is only 10 volts, the fact that this is 50 watts means that it is 10 squared divided by R is 50. 10 squared is 100, therefore R is 10 divided by 100, so it's 1/10 of an ohm. This one is 1/10 of an ohm. All right, let me write it down. 1/10 of an ohm. And now this guy is V squared over R, but now the power used is 100 watts. So it's double. That means that for the same voltage, its resistance is smaller, half. All right. So therefore, what did I have it here? I thought I wrote it down somewhere. Well, you get what did? Can somebody remind me what was the answer? I can't even read my own writing. My pen is. Are you following me? Sorry about that. When I upload the PowerPoint, I will have to put in the actual formulas. Here right now, I cannot write it. This has a higher resistance than this. This is double. This resistance is half of that. And now when I connect both, it becomes parallel. Then it is 1 over the original resistance plus 1 over half the resistance. That means it is 2 over R. So it is 1 over R plus 2 over R. Therefore, the net R is actually R over 3, because there's 1 over R plus 2 over R, so it's 3 over R. Therefore, the net resistance, if I were to connect both A and B, is now a third. If it is a third, the voltage across is still the same. Therefore, now when I put A and B together, I get 3 times. So it's very powerful. A 3-way lamp is, first, it is only 50 watts, then it is 100 watts, and now it is 150 watts. Whatever is the, it's a V squared over R. So it is now brighter. Okay. Well, you can sort it out. And now we just want to sort of like continue on the issue of, if I have a battery, the battery actually has its own internal resistance. So that even though I am connecting it to a battery that has a voltage of 6 volts, the internal resistance is a little r, and the outside is a lamp or whatever is the capital R, then the actual current that flows is not V over R, it is V over capital R plus internal resistance. So this is just, when you are more fussy, then you realize that all instruments have their own internal resistance, and for the battery there is also an internal resistance. It's usually not big, but nonetheless, if you are very fussy and particular, then it becomes an important. And so they have an example where they actually calculate what is the internal resistance. No, they know what is the internal resistance, and then they'll say, what is the actual net voltage across that your battery supplies? It's not the full 10 volts or 12 volts, it is 11.9, because your internal resistance ate up this much of my voltage. Okay, now if you are a electrical engineer, then there are these things known as Kirchhoff's rules. You will not be responsible for it, but just to understand that there is this thing called Kirchhoff's rule, because after all, when I have a current that flows, I need to follow it, and then whatever junction, like in this case, when I follow it, the voltage across here plus the voltage across here must be my total voltage, and this current must be the same current that flows. And there are these things called junction rule, namely when you have a junction, I equal to I1 plus I2, that's the junction rule. And then there's the loop rule, that the sum of the potential drop equals to the sum of the potential across. But you don't have to use it because you are not and I'm not electrical engineer. So we will leave this to the electrical engineer. These are the Kirchhoff's rules. We have in a way already applied it to a simple case. And the galvanometer, we won't work with that. We don't need to learn about ammeters. We don't need to learn about galvanometers. We'll leave it to the actual electricians. But now we want to come to capacitors, because we have already learned about resistors in series and in parallel. We now want to deal with capacitors, and we have time for capacitors. And now for capacitors, I can have capacitors in series or in parallel, but I will start with parallel. I have this capacitor and I have that capacitor connected to a battery. And now I would like to know, what have I done? I have now supplied, because my battery supplied a charge Q to the whole thing. Well, the whole thing, I supplied Q, but part of it came here, part of it came there. So the Q that I supplied is Q1 plus Q2. But then I remember the definition of a capacitance and a capacitor is that if the voltage across it is V, then there is a relationship between the charge, Q1, and the capacitance. So that is C1V, because you told me this capacitor has capacitance of C1. Likewise, the voltage across this other capacitor is the same, because it's been connected to, on this side, to this cathode, and this is the anode. Therefore, the total charge across this second capacitor is Q2 is C2 times the same V, because I have connected it on this side to the same battery. But I know I could not have lost any charge. So Q total is now C1 plus C2 times V, because it is C1V plus C2V. Part of my charge came here, part of my charge came there. Therefore, this now is my equivalent capacitance. All right. So this then says that parallel capacitors, they just add. And you will notice for resistors, it is when into a series that they add R1 plus R2 plus R3 plus R4. But for capacitors, it's when they are in parallel, then they just add C1 plus C2 plus C3 plus C4. It has to do with the basic definition of what you mean by the relationship between the charge and the voltage. All right? Any questions? Okay, all right. But now, what happens when it is in series? Now I have two capacitors, and one is C1, the other one is C2, but I connect them in series. And now, what do I know? I know that there is some voltage across here. Whatever is the current, there's a voltage across here. and there's a voltage across there. But I know that the voltage across here plus the voltage across here must be equal to the total voltage, because that's my supply. I am supplying at the 6 volts, then it may have dropped down to 3 volts, then it will drop down to 0 volts, so that overall is 6 volts. So the voltage across, when I have my capacitors in series, they add up. But then I remember that the voltage for a capacitor is Q over its capacitance, and whatever is Q, it is the same Q. Because if you look at it, this side is plus, this side is minus, and now this side has to be the same charge, because if not, I have either a leak somewhere or I have another wire coming in. So if there is no leak here and there is no wire coming in, the Q of this one must be the same as the Q of that one. And the voltage V2 is Q over C2. So that is Q 1 over C1 plus 1 over C2. And that is the series. When capacitors are in series, it's the opposite. It is inverse. 1 over C1 plus 1 over C2 plus 1 over C3 plus and so on is the equivalent 1 over C capacitance. All right? That's the interesting sort of like algorithm when you have the resistors. When they are in parallel, then it is 1 over R1 plus 1 over R2 plus 1 over R3. But for capacitors, it's the opposite. When the capacitors are in series, then it is the inverse C that add. And now, when you have it this way, and you now want to ask what is the current? Well, the current is the rate at which Q, goes across. So then you have that the current is the same current. Whatever is the current, it now goes across and comes in. Whatever is the current, it goes across and comes back in. But it's the voltage that drops. All right. Now we just end this chapter with some technical aspects of charging of capacitor. It is really for engineers. You don't have to, I will put in also for engineers. But just to recognize that if I am trying to charge a capacitor, I will, of course, connect the capacitor to a voltage source, and I would then be interested in knowing how long does it take to charge this? How long does it take to charge this capacitor, this battery, this whatever charger that I'm trying to charge? Well, there is this thing called time constant. The time it takes to charge is a formula. Now, leave it to the electrical engineers to figure it out, because you do need some calculus to figure it out, to get an exponential. But anyway, what you need is to say, hey, there is a certain time constant, and it is this time constant determines whether it takes 2 hours to charge this. Like my laptop, when it is down and I need to charge, and I connect it to my charger, it will say it will take, let's say about 2 hours to charge. Or my Fitbit, it will say it will take, or my phone, they will say fast charge. It is, takes 2 hours or whatever. That because the people who manufactured it, they already know what is the resistance of the circuit of your charger circuit, and they know their own capacitance. So then they'll say, it will take this length of time. What that means is if your time is, let's say, 2 hours, then after t of this time constant, you have 1 minus 1 over e, and e is 2.78 something. So you would have 2/3. 1 minus a third, that means you will have already 2/3. So after a time constant, you will have already about 2/3 of your charge. And then it will take longer and longer to be fully charged. Have you ever noticed that when you're trying to charge your phone, it will say, oh, it's 1 hour, to full charge, right? But then when it gets to be like, you know, 50 minutes or so, or 60 minutes, they'll say, oh, it will take some more time. And then when they say 2 minutes, you come back 2 minutes, it's still not 100% charged. That's because it is a slow exponential. It gets slower and slower to be fully charged. At first, it was more or less quick. After one time constant, you have already about 2/3. But after that, it takes slower and slower and slower. Have you ever discovered that when you're using your phone, you're charging? Yeah. So just be aware that it's not because my iPhone, my Android, that is they are faulty or they are not sophisticated enough. It's not that. It's rather that this is the characteristic of what the charging is. All right. So don't get mad at them. Okay. So now these. Okay. And let me just quickly end with this slide. There is a few minutes here. The book did not emphasize this, but I want to emphasize to everybody. After all, you have your, is this a microwave oven? No, heater. Actually, a microwave oven. And you have plugged it in. When you plug in your whatever microwave oven, it has its own circuit in there, right? And it has the resistance and it has its own circuit. But one thing that it has that you have to be aware of is that the outside is insulated, right? Because you don't want your microwave oven, each time you go near it, you say, ooh, I touch it, it is electrified, right? So it is not. It is sort of like insulated. However, there can be, and that's where the manufacturer is responsible for it, it can be that sometimes there's a short in the circuit inside. You know what is a short? Inside it's a complex circuitry, but if there's a short somewhere, then the current that now flows is much bigger because the effective resistance now becomes much smaller. So the current now becomes much bigger because your voltage is still the same. It's 110 volts. But if there is a short, S-H-O-R-T, in your circuit, if there's a short, then your one of the circuit now is, this wire is beginning to, it's not supposed to touch the other wire, but because of maintenance issues or something, it now gets too close, and then there is a short, meaning that now the current that flows through this is now 100 times. When it is 100 times, you can then have a short, which now causes the whole thing to be a dangerous thing. You can even have electric fire. So the thing is, be careful that you be aware of this, that you can have issues with shorts. And when you have a household circuit, you have a fuse box. Have you heard of this thing called a fuse box? Yeah. And the idea of the fuse box is if at any point, because one of your appliances having a short, the current flowing through this whole circuit now becomes too big, then the fuse itself burns out and it cuts short so that there is no more current. That is for your safety, because then you'll be able to say, oh, something is wrong. And then you'll have to see which one is your appliance. You unplug one of the appliance and then turn the fuse box back in to see if something happens. Anyway, we are out of time. I will stop here. We will we'll continue on to chapter 21. I will stop here.